Okay, so let's begin with our last lecture here. Okay, so the rest of the students would join. We are just going to go through the recap of what we did in the last class. So in the last class, we looked at how Tomasu's algorithm could be used and ensuring that the precision, that the exceptions remain precise. So we call exceptions as precise exceptions when they behave in the same way as a normal sequentially executing processor would have behaved. So in order to make the exceptions precise, we need to write the results in the right order. So in a normal Tomasulo's algorithm, this was not a concern, and those instructions which were ending earlier could write the results earlier as well. But then we introduced this concept of speculation and running the instruction, executing them speculatively, but committing them only in order. So this for that we need another structure which we call as a reorder buffer. So if we include Tomasulo's algorithm with reorder buffer, this is going to be the best mix. In this case, what happens is that you do out of order execution, but in order commits or in order writes, and this also ensures that all the exceptions are always in precise order in their always remain precise. Then we looked at so one of the topic, the multiple issue processes, including VLIW and dynamically scheduled superscalar processor, was a reading assignment for you people, so you can do it yourself. Then we looked at data level parallelism. So in data level parallelism, there are three different types of you can say designs or architectures that have been implemented in the past and recent. So vector architectures were introduced in 1970s. Then Intel introduced the multimedia SIMD extensions that we are going to study today, inshallah, and GPUs. So GPUs are the more recent versions of data level parallelism, those hardware which are exploiting data level parallelism. So the idea behind data level parallelism is that you want to execute a single instruction on multiple data items. So because that's a single instruction, you just have to generate the control signal once, and there are going to be multiple functional units which are going to carry on their work simultaneously in parallel, right? So this speeds up everything because you do more than one task. Now there is a single instruction, so it's you do a single instruction, but that is single instruction is a big instruction. It has many operations inside it. So you do one task which has many operations, and this always speeds up the process. For that, we just also I have to mention over here, your program should also support such kind of behavior. For example, if you have a program where you have written a code um, which is a recursive code, which is a recursive code in which an iteration is dependent on another iteration, the result of the previous iteration, then such kind of parallelism cannot be, you cannot take any benefit for such kind of parallelism. So for that data parallelism, your code should be easily vectorizable, right? And by vectorizable, we mean that the iterations of the loops that you are running are parallel, and they are not dependent on each other, right? So if they are dependent on each other, then you cannot run them simultaneously. So we also looked at the vector architecture in the last class, and we said that how can we introduce vector architecture in the 5-stage pipeline of MIPS, and if we do so, what other things do we need? So we introduce our own VMIPS processor, a hypothetical processor, which included vector registers, which included different other options, different instructions, and we looked at a program like DexP, how it could be run on a simple processor, and the same version of a vector processor. How would that look like, and what are the benefits going to be? So let's continue with the vector processor. Today we are going to look at two more things: the multimedia SMD extensions and the GPUs. Now, when we talk about vector architecture, there are some questions that come into mind. How can a vector processor execute a single operation a single vector faster than one element per clock cycle. So if you want to, normally what happens in the architecture that we have introduced is that it was a pipelined architecture. So we were doing one operation per cycle, and we were completing one operation per cycle. So what if we want to increase the speed of that and have more than one operation per cycle? How does the vector processor handle programs where the vector lengths are not the same as the length of the vector register? So in the last program, what we saw was DXP, in which there were 64 elements, and we saw that our vector length was also vector register's length was also 64 elements. So we were doing the same thing, which was the length of a single vector. But what would happen if your vector length is something like 100 elements, but your vector register can only store 64 elements, right? So this question also comes into the mind. The third question is what happens when there is a conditional statement. So for example, if you're talking about vector, a conditional statement where you have to do tasks for some data elements, and you don't have to do that particular task for some data elements. But it's both of them are written in a particular loop. How are you going to deal with that? How a vector processor is going to deal with that? The fourth question that comes in mind is what does a vector processor need from the memory systems? Looking at the vector processor and the amount of memory that they need, how big a memory do you need? How can you arrange that memory? The fifth question is, are there any features for multidimensional matrices? Like we saw when we were talking about multiplication of matrices, that one of the matrices was multiplied in row major order, another one was multiplied in column major order. So are there any provisions for special provisions in vector processors for accessing elements from memory? And how does a vector processor handle sparse matrices? So sometimes in engineering application, there are matrices which have non-zero values and many zero values. So you just want to work on those non-zero values, and those matrices are called as sparse matrices. So how can a vector processor work on a sparse matrix, right? So are there any provisions for that? So we are going to look at these 6 questions one by one. Like, how can we execute faster than one element per clock cycle? Now the answer for that is you have to include multiple functional units, right? So if you have got multiple functional units, that's not enough. You have to assign a particular register set to a particular functional unit as well, and these functional units should have different memory locations to store the data so that they can work in parallel. So if you have all of that, that is called as a lane, right? So we introduced the concept of lane earlier as well. So in a lane, what happens is we have got independent set of all the things. So it has a replica of all the execution units, and a portion of registers assigned to a particular execution unit, and a path to get this data from memory. Now, if you talk about this diagram here, so on the left hand side, you can see that we have a single lane vector processor. What happens in a single lane is you can see there is a single adder. This is the adder that I'm talking about here. Okay, so this is the adder, right? So this is our adder, and what is happening over here is it's working on 2 elements, and this is the whole vector register. This whole thing is the vector register, and it takes 1 element at one time. So currently it's working on A naught. You can say it has worked on A naught and B naught, and has produced a result C naught. So currently it's doing this, and it's going to produce a result C naught. After 1 cycle, it will take the next 2 elements after one. So this is the concept of having 1 element per cycle. But if we want to speed this thing up, right? So we need multiple functional units for that case. And the diagram on the right shows here we have got 4 lanes. Now look at the lanes over here. For a lane, you need to have replicas of the functional units. So we have got 4 different functional units. Now, if we have 64 elements and we have got 4 lanes, this means that we can process it in 16 cycles. This is the normal calculation that we can do. Obviously, there are going to be different overheads here, but let's talk about in simplistic term. So what we have is 16 cycles. So 64 converts to 16. This is a 4 times speed up in terms of data processing. But in terms of hardware, you're going to see we have got 4 different adders, right? Not only are there different adders, you can see here there is a different set of elements that are being processed by each function unit. So for example, um, this first one here is actually working on A naught and B naught, right? So I'm just going to write just A naught here. You can see the second one is working on A1. So A1 plus B1 goes to a second. The third one has A2, and the fourth one has got A3, right? So when you have your registers, each register is still of 64 elements. So what you're going to do is you're going to divide your register in such a way that the first element goes over here, the second goes over here, third goes over here, and the fourth goes over here. And then again, the fifth goes over here, sixth, seventh, eighth, and ninth goes over here, right? So in this way, you can see that this first functional unit is always going to have these values 0, 4, 8, all those which are multiple of 4, right? And so on. So and the second one is going to have 1, 5, 9, and so on, right? And likewise for the remaining one. So we have to divide the registers as well. We have to divide the registers as well. Register is still the same register, but the elements of the registers are going to be divided. So the architecture is going to have hardwired connections for particular elements of a register to these functional units, right? And since these functional units are still pipeline, so they are still pipeline, and let's assume they have got a depth of 4 clocks, 4 stages. So what is going to happen is the first element is still going to take 4 clock cycles. The second and onwards are going to take then 1 clock cycles to complete. So as I've mentioned earlier, that is going to take 16 clock cycles. So if I want to do the calculations, it's not going to be actually 16 cycles. It's going to be 16 plus the overhead. That overhead is the additional cycles or stages that we were talking about. Like for example, the first one is going to happen in 4 clock cycles, the remaining in 1 clock cycle. So if you do the maths, there would be 3 plus 16 something like you need not 16 clock cycles, rather 19 clock cycles to finish the task.
So should we add this element group further, C0, 1, 2, 3?
No, this is the answer. This is the answer.
This is the answer.
C vector register. So you see we have got we are doing this task over here. C is equals to A plus B, right? So we need to add elements of, so every C, A, B are 3 vector registers, right? So A has got 64 elements, B has got 64 elements, right? And C is also going to have 64 elements. Okay, so what we are doing here in a 1-lane operation, this is the 1-lane operation, this is the 4-lane operation. So in a 1-lane operation, you are adding A naught, B naught, and getting the result. So it's going to take 64 plus overhead time. The overhead would be 3 cycles. If you're taking the depth of pipeline to be 4 stages, then the overhead would be 3 clock cycles. So when you are going to increase the number of lanes, the overhead is not going to change because overhead remains the same, because that's the time the first operation is going to take. So again, the same thing here, the overhead is going to remain the 3 clock cycles, and you're going to have then additional 16, because every functional unit is then going to see 16 operations, right? So 16 here, 16 here, 16 and 16, that totals up to 64. Is it okay?
Okay, sir.
Right. So now if I increase the functional unit more, if I add more function, like for example, instead of 4, let's go with 8 functional units. So what's going to happen if I have 8 functional units? So if I've got 8 functional units, then likewise we are going to divide the elements which are going to go to the particular adders, these functional units here. But there are 64 elements, so I'm going to divide by 8, and then I'm going to get 8. So I have reduced the time, or that I have, you can say, reduced the number of cycles to do these 64 operations. So it would be 8 plus the overhead. That overhead is still going to be 3. So that overhead is still is 3 in this case. So this is going to be completed in 11 cycle, right? So from 64 plus overhead, you have moved to 16 plus overhead, you have moved to 8 plus overhead. The problem here is that you are increasing the cost of the system, because as you are introducing more hardware units, then you are increasing the cost of the system. So there is a trade-off of how much cost that you can increase, and what is the performance that you need. So if you have more functional units, you can do it in less time, but the problem here is, do you have more data that can fill in these, that can make these functional unit busy at all times. So for example, it can do it in 11 cycles, but what's going to happen next? Do you have enough data to feed these adders, to feed these functional units? So for example, you don't have much of those instructions to execute, or you can say your memory is quite slow, then it cannot provide you with the data at the right time. So that's not going to benefit you. So what is beneficial is that you have to make an architecture or make a design in which, if you are including more functional units, then that should be supported with uh, more bandwidth from the memory side as well, right? Okay, so this was the first question, that if you have got multiple lanes, then you can obviously do the operations, more operations in one cycle. This is another view of what a lane would be. So if there are 4 lanes here, so you can see here, here is a whole the whole replica of a lane is included. The whole elements that are needed in a lane are replicated in all these 4. So we have adder over here, an adder over here, a multiplier over here, and a multiplier over here. So and vector register elements. So every one of these lanes have separated their vector register elements. So 048 is going to work over here, 159 is going to work over here, and then each one of them have their own load store units to fetch the data from memory, right? So this is how a lane is going to work independently. So it's going to work independently from the other lanes, and that is how you are going to work faster. The second question is, what is going to happen if we are going to work on elements which are not the size of the vector register? So here we have talked about a vector register which is 64 elements wide. Now there can be 3 things that are going to happen. So if I just, yeah, so if you have n number of elements to work on, then n can have 3 different values. If your vector register is having a size of 64 elements, then n can have 3 different values. N can be equal to 64, right? N can be less than 64, or n can be greater than 64, right? So these are 3 possible chances. So what we looked at last time was n equal to 64. So we saw that we needed to work on 64 elements, and the vector register length was of 64 elements, so everything was fine. But what if we have just 50 elements to work on? Your vector register has 64 elements. It fetches 64 elements. It works on 64 elements because your pipeline is designed in such a way that it's always going to work on 64 elements. So what if we only have to work on 50 elements? What if we have to work on 100 elements, right? Now when you go for the sizes greater than 64, again there are 2 possibilities here. If you are working for elements which are greater than 64, then you have elements which are multiple of 64s, and then which are not multiples of 64. Like for example, 256. 256 is a multiple of 64. It's also greater than 64. It's a multiple of 64 as well. But 1000 is not a multiple of 64. So if you want to work on 1000 element or 100 elements, it's still greater than 64, but it's not a multiple of 64. So what are you going to do in each of these cases? So we just looked at this one over here in the last class. Let's talk about what's going to happen if you need to work on less elements. So this is, for example, a code here defined for I is equals to 0, I is less than n, and I plus plus. So we don't know what this n value is. So right, so maybe this is part of some it's a parameter which is going to come from user or maybe something else. So this is not known at compile time. So what are you going to do in that case? So n can be different things. So if you want to code your system, how are you going to do that? Now in vector registers there is a special register which we call as the vector length register, right? So a vector length register is going to define how much are you going to work on, how much elements are you going to work on. So there are two different registers. One is a maximum vector length register. Now this is, you can say, a hardwired register, a hardwired constant. You can say this is always constant for a particular architecture, right? For example, in our case, the maximum vector length is 64. So it's going to work on 64 elements. Now, whenever we have a maximum vector length of a particular number, the control unit is going to generate signals for that much amount of time or that much amount of elements. So for example, if you just change the maximum vector length from 64 to 128, the control unit is now going to generate signals for 128 elements to work on 128 elements. So this is one register, maximum vector length. Then there is another register, vector length register. Now vector length register can have value which is less than or equal to maximum vector length. So it can never exceed the value of maximum vector length, but it can be less than the maximum vector length. So if your VLR is set to the maximum vector length register, this means you are working on all the 64 elements. But in this register can be reduced. So you can set it to a particular number less than the maximum vector length, and then this would mean that all your vector operations, the same operations that you have defined, like add vector vector, it's going to work on just the first 50 elements of that vector register. Okay. Now this is a special thing in vector registers. We introduce a vector length register, and this registers could be changed. So you can change that before any program, and if you're going to change that, all the next vector instructions are going to look at this vector length register and are going to work accordingly. But if you are going to change that back to 64 or maximum vector length value, then all these instructions are going to work on 64 elements, right? So in vector processors, we have a vector length register, and this register size could be, this register content could be changed. So if you are going to work on just 50 elements, then it's going to just work on those first 50 elements, right? So you are going to write the same program, but before writing that program, you are just going to change the vector length registers content from 64 to 50, and then it's going to work on first 50 elements. So if you have two vector registers, so for example, you want to work on 50 elements, and this is vector 1 and this is vector 2, right? So if you want to work on first 50 elements, so you just have to change the vector length register, so it's going to work on just the 50 elements. What about the rest? Because you have set the vector length register to be 50, then the other elements are not going to be stored, or you are not going to work on them. Now, does that mean that we are going to take 50 cycles to do our task? That's a different thing, because your pipeline designed in a way that it's going to work on maximum 64 elements. It might happen that you are still going to take 64 cycles, but for the remaining 14 elements, you are not going to work, but you are just going to go through those functional unit without doing anything, right? So that depends on the architecture. The main thing is the results for this the 50 elements are going to change. For the remaining these vector, for example, if you want to add these two and you want to store it somewhere, and that is also 64 elements, so the only the first 50 elements would be stored, the remaining are not going to change, right? So this is how you can say you have just worked on 50 elements. Okay, now we come to the second point. What if the number of elements are greater than the maximum vector length, or 64 in our case? Then again, as I mentioned, that there are two different types of two different ranges here. One is that you can have numbers which are a multiple of 64, like 128 or 256 and so on. Now for such kind of elements, it's easy, because if you have got 64 as your size of one register and you want to work on 128 elements, you just have to do that operation twice. So you're just going to write a for loop, right? You're just going to write a for loop. So you have loops also in vector registers, vector processes, and you are going to do 64 elements each time, or because these numbers are multiple of 64, so either you are going to do it 2 times or 3 times or 4 times, whatever, right? So you are just going to run that loop as when time as required for such kind of numbers. But what about if it's not a multiple of 64, like 1000? So what to do if it's not a multiple of 64 or your maximum vector length? So what you do is strip mining. Now when you talk about strip mining, what happens is we define two different loops, and we work on the first such elements which are not multiple of 64 or vector length, and then we work on the remaining elements. So if I give you an idea of how this is going to happen, so for example, let's talk about 1000. Now what we are going to do for such numbers is, first of all, we are going to look at the closest multiple of 64, the closest multiple of 64 which is less than 1000. So if you have your calculators with you, so I can just see if I have if I can we can do this over here. What we need to do is we just have to uh, divide 1000 by 16, and we are going to get some number here. Is that 62.5? So 62 is our number. So what is 62 into 5? So 62 into 16, sorry, 62 into 16 is 992. So we have divided 1000 into two different numbers, 992 and then the remaining 8. So 1000 is actually 992 plus 8, and 992 is actually 62 into 16. Why have I divided by 16? Sorry. sorry, not 16, 64. We were working on 64 elements. Okay, so 64 elements. So 1000 divided by 64. Yeah, 15.625. So 16 is 15 is our number here. So 15 means if you're going to have 15 into 16, 60 again 60, 64, it's going to be 960. So 960 and the remaining. So we have divided 1000 into 960 and 40, right? And 960 is actually 15 into 16. That's the number which is the most closest to 1000 and still less than 1000, right? And it's it's a multiple of 64. I'm writing 16 again and again. So 64, 15 into 64. Okay, so what we are going to do now is we are going to have two set of operations, or you can set two loops here. The first time we are going to work on these 40 elements, right? And the way for that is we are going to set the vector length register to be 40 in our first loop, in our first iteration. Then what we are left with after 40 is a number which is a multiple of 64. So then we can do that those elements in changing the vector length register back to 64, and doing that in another loop which is going to repeat 15 times. Okay, so this is how we can do it on 1000 elements. So 1000 wasn't a multiple of the vector length, which is the maximum vector length, but what we did was we divided into two different set of elements. So we are going to get, so you can say in other words, if n is your number, then you just have to divide it by maximum vector length, right? So you're going to get some quotient part here, right? And you are going to get some remainder over here. So remainder is actually this thing here, and quotient is the number of times that you have to repeat it. Okay, so number of times you have to repeat this loop. So this is then n, or you can say this is n divided by mvl, and this is n mod mvl. Mod is the remainder operator. So m mod mvl and m divided by mvl, m divided by mvl, and take the floor of that function. I'm going to make it a little clearer. So what I'm saying is n is your number, so you are going to divide in two things: n divided by mvl, take the floor of this function or the smaller integer, and the other set is then n mod mvl, right? So this is how you can separate these two out. So if n is 1000, mvl is 64, divide 1000 by 64, take the floor of that, take the integer part. So you're going to get 15 over here, and then n mod mvl is going to be 40 over here. So you 15 is going to be the number of times you're going to repeat that operation, and then 40 is the remaining. But we are going to do first on 40 elements, and then we are going to do, so this method is called as strip mining. So what we do is one loop is created that handles any number of iterations that is a multiple of mvl, and another loop that handles any remaining iterations and must be less than mvl, right? So this is how you can do for any number you want. So in practice, what happens is you make a single loop which is called as a strip mine loop, and an example for that is shown over here. So you can see what's happening over here is this is your vector length register, which is initially set to n mod mvl, whatever that value is, right? And then you are going to work from j is equals to 0 to j is less than equal to n divided by mvl, right? So you can see over here is less than or equal to, meaning that it's going to run one more times because you are starting from 0. So the first time where the value of j would be 0 is when you're having vector length as 40, right? So you're going to work on 40 element. Low was initially set to 0, so I from 0 to 40 you are going to work on the first 40 elements, right? Once you have done this thing on first 40 elements, what you're going to do is change that to 40 plus your low, which is going to be, in this case, since low is going to be low was 0, so 0 plus vl is 40. So now you are going to have a low value of 40, right? And vl you are going to change it to 64. So now what you're going to do in the next iteration where j is equals to 1, you are going to start from 40, and you are going to go to 64 plus 40, that would be 104. So you are going to go for the next 64 elements. So because now you have changed it to 64, so now you're going to work on 64 element. This here is going to be converted into a vector instruction. So this is what we saw in the last class. This was a DexP. This is a DexP program here. This is a DexP instruction. So this is going to be converted into appropriately 4 or 5 instructions. So this is how you can do it. So you can see here we have a single loop that can do these tasks for 1000 operations. So graphically you can see that the first iteration with its value of j was 0, you have done work for 40 elements. Then you're going to go to in each iteration 64 elements, right? And this is going to go maximum till 15 in this case, right? So this is how it's done, right? So this was about a vector number of operations in a vector processor. Now, what if there are conditional statements in our program? So what to do in such a case? Because in a program like this that we saw earlier, what was happening was, if I go back 2 slides or 3 slides maybe, yeah, this way, this program here was about, you can see here there is no conditional statement in this program. This, we are going to convert this program into a vector, its corresponding vector version. So you can see here there are no ifs over here, so you're working on all the elements of that element. But what if we have got some program where we are calculating, um, say for example, we need to find the magnitude of, of, uh, of of elements present in a vector. So they are going to be numbers which are negative. They are going to be numbers which are positive. So if it's positive, it should remain positive. But if it's negative, then it has to be converted to positive. So what we need is, if the number is only negative, then you are going to convert it to positive, right? So this is not going to be for all of these elements. You are just going to change the sign for those elements which are negative. Now this is a problem where we have conditional operations here, right? So how are vector processors going to deal with such a problem? Now for that, what vector register have is called as a vector mask register. Now what happens is, we set the vector mask register, and a vector mask register is a simple register which has got a single bit for every element. And if you want to work on that particular element, you have to set that bit to be 1. If you set that mask to be 0, then that element is not going to be operated on, right? So what we do is, if there is a conditional statement, we first of all set the vector mask register before doing our operations. And once we have completed our operation, we can then remove that mask, right? So I'm going to give you an example. So for example, we have a program like this. So for I is equals to 0 to 64, what we are doing is, if the particular element is not equal to 0, what we are checking is, if it's not equal to 0, then you need to subtract it from y. If it's 0, then you are not going to subtract it, right? So this is our way of doing things. So again, but the problem here is, there is an if statement over here. So what we are going to do, we are going to have a vector mask register. So we have got 64 elements. A vector mask register is going to be a special register which has got 64 entries, and each entry is a single bit wide. So it can either hold a 0 or a 1. When you have a 1 corresponding to an entry, this means that entry is going to be worked on. If you have a 0 over here, that entry is not going to be worked on, right? So how are we going to proceed for such a program? We first of all, we have loaded the whole vector register in a register, the whole 64 element, all those 64 element in the register v1 with a normal vector load vector instruction, and we have also loaded y into v2. So we have both our registers ready. And since it's working on just 64 elements, we can just do a single operation to complete our task. But this is not simple, because it has got a conditional statement. So first of all, we have to set our mask. Now, since we are checking it with 0, what we have done is, we have loaded the value in a floating point register. Now, this is the main instruction which is going to set our mask. Remember, we saw this instruction earlier. This instruction, when we were talking about the set of instruction in our last class, we saw an instruction which was something like this, which has got 2 different blanks. And I told you that these blanks could be filled with different values. Here we have filled it with NE, which is not equal. So not equal means that you're talking about vector and a scalar operation. So if there's this vector with corresponding scalar, so this scalar is going to be compared with every vector element. If they are not equal, then it's going to set the particular element's mass to 1, right? And this is what we want. So if they are not equal, then only we are going to work on it. So we have to set our mass for 1 for those elements which are not equal. If they're equal, that mass is going to be set to 0. That is, if any element is 0, then that corresponding bit of the vector mass register is going to be set to be 0, right? And then what we do is do a single operation, subtract vector vector. Now this single operation is going to work only for those elements which have their corresponding mass bits as 1, and it's not going to do any other operation. And when we want to store that result back to v1, then we can do that. And since the mask has been set over here and it has not been cleared yet, then what you can do assume is that all operations afterwards are going to look at this same mask register. So if you want to do now work on all the remaining elements, you have to clear this mask that has been set over here, right? So if it's not cleared yet, then you have to all these operations are going to work on only those elements which have their entries having ones. So even with this store vector element, it's going to store only those results which have their entries as 1, right? So this is how you can do conditional execution. So you can see here it's very easily done in a vector processor using the same instruction. Before that instruction, you have to set the mask, and once the mask is set, then you can apply that instruction. Okay, so what does a vector processor need from memory? Because as we know that there is a lot of demand for data elements. You need to process more data elements, so you should also have sufficient memory bandwidth to support the vector processing. So we're going to take an example of the Cray processor. That was a vector processor T932. So this processor got 32 processors, and each processor was capable of generating 4 loads and 2 stores per cycle, right? So 4 loads and 2 stores per cycle for 32 processors, right? This means that there are going to be a lot of memory operations. And if all these 32 processors start generating 4 loads and 2 stores per cycle, the processor cycle time was 2.167 nanoseconds. So the processor cycle time, when you're talking about one cycle, so that cycle that the processor is seeing is 2.167 nanoseconds, while the SRAM cycle time was 15 nanoseconds. And the cycle of SRAM, what the memory was seeing was 15 nanoseconds. So every operation from memory side was completing in 15 nanoseconds, but this processor could generate 2.167 nanosecond, 4 load plus 6 memory operations per 2.167 nanoseconds for a single processor. So you can do the maths, it multiply by 32 to get the whole picture. So the question is, how many memory banks are needed over here in this case, in this particular case? So how to calculate that and what? So if we assume to design a memory for such a system, the first thing that comes in mind is let's go with the best case. And the best case is that whatever these processes are generating are going to different memory banks, right? So if they are obviously going to be many banks here. So and they are going to generate different requests. So let's assume all these requests are going to different banks. So whenever you give a particular request to a bank, it takes some time, and that time in this case is 15 nanoseconds. So if you generate another request for the same bank before 15 nanoseconds, then that request has to wait. But after 15 nanoseconds, since the memory has sent the data, then this memory is available and you can generate another request. So what we are assuming in this case is that whenever we are going to give anything to a particular memory bank, the next thing that's going to come to that same bank is always going to be after 50 nanoseconds. This is one thing that we can assume over here. So let's do the math over here. So we have got 32 processors, and each processor is generating 6 memory accesses, that is totaling to 192 accesses, right? So in total we have got 192 accesses, right? Now if you take a comparison of what the memory cycle time is and what the processor cycle time, you see that they have a difference of 7 processor cycles in between. That is, these accesses are for one cycle, but if you want to give it to the bank and that bank should complete its task, this means that for 7 more processor cycle this bank should not get any more tasks, right? So this would mean that if you're going to multiply the number of banks that you need, it's going to be something like 1344 banks. You just multiply 192 by 7. So this means you need actually 1344 memory banks, different memory banks, separate independent memory banks that can work together, that can work separately, independently. Actually what was there in this gray processor was it has got 1024 memory bank, which is the closest figure of a multiple of 2, right? So 2 raised to power 10 is 1024. It's always better to have it in the powers of 2. So what we did is, according to the worst case, when every processor is going to generate accesses, but the best case in another sense, that we are saying that these requests are always going to go to different banks. So we are assuming that what is the difference between the processor cycle and the memory cycle. So this means that processor is going to generate 192 into 7, that is 1344 different accesses in a time where that memory is going, where the single bank is going to complete this task, right? So this means that if you don't want any conflicts, then you need at least 1344 memory banks at the least, right? Anything lower than that is going to create banks, so conflicts. So we have a number which is lower than this, but in this we are assuming that not every processor is going to generate 6 memory operations every cycle. So this is the peak demand, and we are assuming if that peak demand is not going to happen, then obviously we are not going to get any conflict. Otherwise, if the peak demand is going to be implemented by all the 32 processors, then these number of banks are not enough, right? So this means that in a vector processor, the memory bandwidth is very main concern. So you need a memory which has got enough bandwidth to support the data. Okay, so let's finish the vector processor by 2 more questions here. What happens if we have got multi-dimensional vectors, multi-dimensional matrices? So like a matrix operation. So how can we get data which are stored in a different way? So remember when we were talking about um, matrix multiplication, we saw that one of the matrices is going to get the data in a row major order, another is going to get the data in a column major order, but these elements are all stored in row major order. So for such a matrix, it would be easy because all these elements are stored consecutively in contiguous locations. So you just have to fetch all the next elements and bring them in a single register, and that's it. But when you have to fetch instructions which are in a column major order, they are stored in a different way, because if you want to see how it's going to be stored, the first element is going to be here, the second element is perhaps here, the third element is perhaps here. So they are not in contiguous memory locations, right? So the question is there any feature in vector registers for such kind of memory operations that if we need to fetch elements which are not in sequential locations, in contiguous locations, and can we bring them in a single vector register such that the first element comes over here, the second comes over here, the third comes over here, right? So is there any way over here in vector processor to do such kind of operation? Yes, there is. Okay. So you can see over here, even with this particular memory access, there is something which is good, and that is the difference between every element, and that is a constant. So that is a constant. You have got um, same number of elements between these two elements. So that is always going to remain the constant. We call this constant as the stride. So we call that as stride. That's mentioned in the slides here. So that's the stride value. So in this case, the stride value is a, right? So we need to fetch every element after a elements, right? So for that, we have a special load vector instruction. We call that as load vector with stride. So just you have to provide the value of stride. Like in this case, you're just going to provide the value of stride as a. So it's going to fetch only after every a element and bring those elements in memory in a vector register in its dense form. So it's going to take these elements from different places of memory, but these places are not random places. They are at a distance of a elements from each other, and then it's going to bring them together in a single vector register, where the first element is going to be over here, the second over here, and third over here. Now what you are just left with is simple multiplication of these elements together, and you know that every first element of the row is going to multiply first element of the second matrix, and then the second element of the row of the first matrix is going to multiply with the second element of the column of the second matrix. So since both of them are now in the register, these can be done. This operation can be done um, in a single operation. Um, so once you have these two in separate registers, V1 and V2, the next thing you need is do one operation, which is V1 multiplied by V2, and that's it. Right? So since it has brought all the row elements in V1 and it has brought all the column elements in V2, what is left now is do single operation V1 into V2, which means that the first element here is going to multiply it with this one, the second element is going to multiply it with this one, and so on. Right? So this is as simple here. This is a program which is showing how this can be done using stride values. So this is a program which we want to implement, and this can be done using load vector with stride. And then there is another corresponding instruction, store vector with stride. So load vector with stride and its corresponding store vector with stride, it has the other effect. Store vector with stride, you are going to provide the value of stride over here in this case. Obviously, it's going to be there are going to be bank conflicts if you hit the same bank faster than its busy time, right? If you have because you're talking about taking elements which are at a distance of certain elements between them, then this thing is easy to do, because what happens is these consecutive elements are going to go to different memory banks. So how if they are stored in consecutive location, normally what happens is you have got many memory banks. So the first element is going to be stored over here, the second would be over here, the third would be over here. So if you want to fetch the consecutive elements, you are going to give accesses to different memory banks, right? And this is how you can fetch these. But if you want to access elements which are at a distance from each other, like this and this, so it might happen that these two are actually in the same bank. So if you want to access this and then you want to access the next one, this might create a bank conflict, right? So we have talked about that early. This is called as memory interleaving. So when you store consecutive element, you store them in different banks. So memory, if you are doing a memory interleaving, then this is going to work for consecutive elements, because these are stored in separate banks. But these are not consecutive elements in this case. If it can happen that all these elements are basically stored in the same bank. So if you're going to access them, then it might result in in larger access time. If all of these values are going to go to the same bank, then it's going to create a, a problem for you. For example, if you have got 8 memory banks and you want to access the 0th element, the 8th element, the 16th element, because your stride value is 8, then all of these elements are actually going to be in one bank. So that's the problem over here. So if you have got 9 banks, that's not going to be a problem. But if you have got 8 banks, then 0, 8, 16, all of them are going to lie in the first bank, right? Because you have got 8 banks, so all the zero element is going to be here, the first is going to be here until the 7th element, which is going to be here. The 8th element is again going to be over here. So, and if you want to fetch only these elements, then all of these elements you are going to find in a single bank, and this is going to create a problem. So you can get different problems over here if the number of memory banks are a multiple of the stride value, right? So if the stride value is 8 and you have got 8 banks, then it's going to create problems. Right, let's come to a last question. What about sparse matrices? So what actually are sparse matrices? Here's an example. We have got matrices which have got many non-zero values, and we need to work on these non-zero values. Sorry, which has got many zero values, and we don't need to work on these zero values. We just need to work on the non-zero values. So we need to work on only these values. So for that, what happens is when you're going to store a sparse matrix, you store the index value also, where in this matrix is a non-zero value stored, and you need to work on only those values. So is there a way for that in vector processor? Yes, there is a special instruction to work for these matrices. We call that instruction as gather and scatter. So there is another load type in vector processor. What happens in a gather operation is you need a vector index vector, and it's going to fetch all those elements which are provided over here. So if I come back to my early example. Now, when you're going to store this thing, one way to store is to store the whole thing together. The whole matrix is going to be stored in memory. But along with that, another index vector is created. This is normal with sparse matrices, that you always create an index vector. And this vector is going to have values of those non-zero elements. So for example, if this is 0 and this is 1, so you're going to store 0, 1, 2 is a 0 value, 3, 4, 5, 6, 7, 8 is 0, 9, and so on, right? So you have got an index vector as well, so that when you are going to look into this, you can just directly access all these non-zero elements using this index vector. Now, how can vector processors do this? They have their gather and scatter operations. So what happens is they need this index vector. So they are going to load that index vector, and then it's going to load that particular vector according to that the elements over here into using as load vector with index instruction. So this is that instruction, and it needs another vector. So you are first of all going to load that index vector into a vector register, and then using the simple load, and then you're going to use load vector with index. So it's going to fetch only those elements which are provided in the index register. This is again a special instruction in vector processors. Scatter, on the other hand, is going to do the opposite. It is going to store that in those elements which are provided by the index. So you can go through this program, which is actually doing this. It's adding two sparse matrices, but both of them have same number of elements. So one of them has elements in ki vector, and another one has in mi. So first of all, you need to load ki and mi into separate vector registers, and then use load vector with index, and then you are going to get a dense matrix, a dense vector in this vector register va and vc, and then you can do your addition operation, and then you can store it back, right? So this is a simple example over here. So once you have done all of that, then you can go through this. It has got different other instructions like cvi that we have not studied, pop, right, mtc, right? CVM. So we have talked about that. Like this is clearing the mask. This is about loading the vector length register that we have said that we can do it with different values. And this is about pop, another special instruction which can find number of ones. So this is about vector registers, vector processors. This was about vector processors, and I'm going to stop over here. If there are any questions related to that, this should have been completed in our last lecture, but since we are getting because of this online classes, we are a little late. So normally what I do,
Sir,
yeah,
sir, you have only fetch non-zero values in the matrix which we have shown in previous slide.
yes.
But where you have mentioned 0, 1, it's okay. Then you have mentioned 7, uh, 0, 1, and then 7. Can you
Okay,
come on this?
I'm just going to come back there. If I have made a mistake, I let us see.
Uh,
Right, so we are going to have 0, 1, 2, 3, 4, 5, 6, 7. 7 is again a non-zero value, right?
okay, 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 okay. 7,
8
8,
and 9,
9.
right? So they are all
Yeah.
non-zero value.
Okay. You mean starting from 0?
Yeah,
It's
they're starting
okay.
from 0.
No, I'm starting from 1.
Actually,
Sorry, sir.
actually, there are different formats for storing sparse matrices. You can search that yourself. One of the common format is CSV is also one of them. Um, the comma separated values. There is another one. I'm not sure about that, but it's quite common. So what it happens? It has a little different way of storing these parts matrices. You can search that on the net. It creates another vector as well, which is it calculates by the rows as well. Okay, how many non-zeros were there in a particular row as well, and that it stores that thing as well. Anyhow, but that's a separate that's stored in a separate element over here.
So for it, we have to write a program
Um, for what?
in order
If
to.
you're working on a sparse matrix, then obviously you are going to deal the sparse matrix in a different way. Where are you going to see sparse matrices? So you see them in different other application, like sometimes in images as well, right? You want to do a transform of a particular image. It has got many non-zero values and some and many zero values. So you don't need to store those zero values, or you don't need to work on those zero values. That's a more important thing. You're still going to store them, but you don't need to work on them. So if you want to work, if you are going to include that into a calculation, it's going to just waste time. So for example, if you want to increase the intensity of these elements over here, but you're just talking about non-zero elements, so you need to work on only these elements, right? But if you want to if you are going to include these elements also in your calculations, but you're not going to do that anything on them, then it's just going to waste time. For example, you want to multiply some with a factor, but anything multiplied by 0 is going to be 0, but still you are going to multiply it, so you're going to waste time. So the better thing is that you select only the non-zero elements and do your task on them, right? So that for that, you if you're working on sparse matrices, there's a way for that. So you are going to work on non-zero matrices, non-zero elements only, and for that it's going to store the whole sparse matrix, as well as it's also going to store the index vector. You're going to fetch that index vector. You are going to fetch the non-zero elements using this index vector by a special instruction that we have just studied. It's called as LVI, or load vector with index, right? So it needs the vector register, it needs an index register along with that vector first element, first area. So this RA is basically pointing to, so if you have got a matrix, RA is basically pointing to the first element of this matrix, and RK is stored somewhere else. It's pointing to the first element of that index vector. So what's happening is these, it has got the numbers. It's going to add that value to RA to get to that particular element. So 0th element, first element, 7th element, 9th element. So it's going to fetch only these ones, and when it's going to fetch them, it's going to combine them in a dense form. So the sparse matrix converts to a dense form. The first element goes over here, the second over here, the third over here, the fourth over here, and so on. So once you have all these non-zero elements together in a single vector, then you can operate on them quickly. Okay.
Okay, sir.
Right. So this was about vector processors. Let's come to our next topic, which is the SIMD instruction set extensions. So as I mentioned here, vector processors were the earlier ones, and they had a lot of hardware requirements. But when talking about desktop systems that were introduced by Intel in 90s, they wanted to have a flavor of vector processing also in them, because vector processors exploit data level parallelism. So if you want to do that at a smaller scale in a desktop processor, how can you do that? But before going through that, let's talk about another concept over here that can be useful in thinking about vector processing. Now let's say we have a hardware, we have an adder. So we have already studied adders earlier. So let's say we have got a 64-bit adder. So what a 64-bit adder is going to do is going to take a 64-bit number, another 64-bit number, and it's going to give you a result of 64-bit, right? You all know how an adder is going to work. Now let's assume that I'm not going to give it a 64-bit number, or it's actually a 64-bit number, but it's actually that number can be stored in a single byte. But I have an adder which is of 64-bit, a 64-bit adder, but my number that I'm giving is of 64 bits, but it's actually could be stored in 8 bits as well, right? So it has got many zeros, and the last byte has got that number. So if, for example, if I need to add 8 with say 64, so both 8 and 64 can be stored in a single byte as well, right? But since you have got an adder which is of 64 bits, you are going to have 8 on one side, 64 on the other side. You are going to get an answer 72 as a 64-bit number, right? Now this is what can you think of this? This is totally wastage of resources, right? Why? Because you have got such a big adder and you're just doing a single byte addition on this. Okay. Now, but that's the only thing that you can do, because it's a 64-bit adder, and you can obviously use 64-bit adder for doing every type of calculation. So even if it's a single byte calculation, so if you have got many operations which are of single byte, like for example, if you have got an image it's an intensity image, and every pixel's intensity is stored in a single byte. So it can have a value say from 0 to 55, and that's a single byte. That can be stored in single byte. So it's an image having many pixels, and all these pixels have, and you want to increase that pixel density, that pixel intensity, by a constant like say 40. So every pixel's intensity should be added with 40 and then stored back. How can you do that in such a adder? So what you're going to do is you're going to take the first pixel, add 40 to it, and store it back. Second pixel, add 40 to it. So you're doing one byte at a time. Okay, even though what you have is a 64-bit adder with you. Now what we can do now, let's now talk about how we can improve this operation. So what we can do is think about how can we improve this operation using the same hardware without changing much in this hardware. How can we improve it? So what we can do is we can have some kind of separation in this adder if possible, and if we break the chains of this adder after 8 bits, so that we have got 8 8 bits adders. So if we have got 8 bit adder, that's still a 64-bit adder. So what we are doing saying is that normally in a ripple carry adder you have ripple effects going on through the whole adder. In this case, what we are doing is we are not going to propagate the adder after every 8 bit, not propagating the carry after every 8 bit. So this is not going to happen, and this is also not going to happen. So within these 8 bits, they are going to be carry chains, but not in these. So what you have converted is a 64-bit adder into 8 bit adders. Is this okay? Is this okay? So we have converted a bigger 64-bit adder into smaller adders, but more of them, by doing just one thing, that we are not going to propagate the carry from the 8th bit to the 9th bit, and from the 15th bit to the 16th bit, and from the 23rd bit to the 24th bit. Okay, I need an answer. Is this okay? Come on. Have you got this point? Did you get this point? Come on. Are you getting my audio?
Yes, sir. I'm still
Yes,
getting,
sir.
sir. Moment Ijazat.
Yeah. So why are you responding only on these things? Are you getting my audio but not on the other things? Okay. So yeah. So this is the main thing that I've said. So if we are going to do this, then what are the changes do we need? So what we are going to do, once we have broken our adder down into in such a way, what we are going to do is, um, let me just come back to that. What we are going to do is, instead of providing it with 64, a number of a single byte as a 64-bit number, what we are going to do is just provide 8 bits and provide a bigger number, convert the number into 64 elements. So what we are going to do is take first 8 elements, merge them together into 64-bit number. That number is going to be a 64-bit number, but it has got 8 numbers embedded into it, right? So we have okay, let me give an example. So we have got 4 and 6 and 12 and 13. So let's talk about 4 of these numbers. So what I'm going to do is make a bigger number which has got all these together, 13. I'm just talking in decimal because easy to understand. You can think about the same thing in binary terms, because each of these 4 bits, each of these 8 bits are separate numbers. Now this is a 32-bit number, right? If you want to write it in binary, you can just write 13 in 8 bits in binary, 12 in 8 bits in binary, 6 in 8 bits in binary, 4 in 8 bits in binary. So altogether it's a 32-bit number, but it has got 4 numbers embedded into it. Okay. So likewise, what I'm saying is you can do it for 64 bits. So in that case, there would be 8 numbers embedded in this bigger number. So you're again going to provide this number on one of its input, and another number which is again going to have 8 different elements in this as the second input. So what actually you're doing, okay, let me just clear this thing. It's not okay. It's so much confusing. Let's do it again. This is my adder. This was my adder. I have broken it down into 8 different. Broken it down means that I'm going to have a special feature in this adder which is going to stop propagating from every 8th bit to the 9th bit. Okay, so this provision is going to be a special provision, and I'm going to apply this provision occasionally. Whenever I need, I can do that. So it's not going to propagate from 8th to 9th. This can be stopped from 15 to 16, likewise, and so on. So in this way, what I'm going to do is, if I have pixel intensities as a single byte, I can merge them together into a big number, give that as one of its input, another number which I need to add with all of them. For example, if it was 40, I need to create 40s, many elements of 40, and give it as a second number to it. And then this adder is going to work and give me some results. Now, what is that result going to be? This result is going to be the first number added with the first number, the second number added with the second number, and so on. Why? Because I have removed these carries, these ripple carries effect. So this means that every 8-bit is going to be a separate number. Okay, so it's going to be treated separately. So what I have done is converted this 64-bit adder into 8-bit adders. I've converted the 64-bit bigger adder, which can take 64-bit number, and I've converted into 8 adders, which can take 8-bit numbers. I'm going to still give it the 64-bit number, but this number has got 8 elements in it. And it's going to add a 64-bit number with another 64-bit number, but actually what I'm doing is I'm doing 8 operations together. Is this okay? So the same concept here is applied in SIMD extensions, is that we have got special instructions. ISX means instruction extension. So SIMD instruction set extensions. So it started with the observation that a 64-bit word can fit 8 bytes of pixel intensities and 4 16-bit audio samples and 2 single precision floating point numbers. So if you can do this, you can use the same 64-bit adder to do these tasks as well. You can have 8 bytes of pixel intensities added together. So yeah, you can have 8 operations of byte level, 4 operations of a 16-bit word level, and 2 operations of a single precision floating point level together with this 64-bit adder. Okay, and if your adder is a little more wider than this, for example 256-bit wider adder, then you can do more operations. So you can include 4 floating point of 4 double precision floating point operations over here. Okay, so it started with MMX. First of all, just give me a response. Did you get this thing? Because it's easy to understand. I don't think so. It's so much difficult, right? Okay, thank you. So history of SIMD. So what started in '96 with this the Pentium processor. The Pentium processor, the initial processor, had MMX technology. It was called as MMX technology. These MMX was actually multimedia extensions. So multimedia, because most of the time we are doing multimedia operation like in graphics, in audio. So, and it was done for only integer. So it was a multimedia extension called as multimedia extensions. And then later on, with the introduction of Pentium 2, this was converted. More instructions are added to the existing set, and this was called as a streaming SIMD extensions, right? So in 1999, the register width was increased to 128-bit instead of 64-bit, and you can obviously do more operations. So it was called as streaming SIMD extension. The previous extensions were still there, and you included more into that. Then in 2001, Intel introduced SSE2, which added double precision. Then in 2004 and 7, it added more instructions to the already existing set of instructions. And then in 2010, AVX, or advanced vector extensions, were included, which were doing operations on 256-bit registers. Now, if you want to compare that with vector architecture, as you have seen here, this is a vector operation at a very small scale, right? So we can compare this SIMD extension to vector operation, but it's a very small scale. Normally what we have is a vector register containing 64 elements of 64-bit each. Here we are talking about just 8 elements of 8 bits. So it's a single 64-bit register which is containing 8 elements of 8 bits. So you can't just compare the size of these two operations. So it's a vector operation at a very small scale. You can talk in this term. The other thing is it hasn't got any provision of masking. You cannot do conditional statements over here. It hasn't got any sophisticated addressing mode like strided access, which we did for multidimensional matrices, or gather scatter that we did for sparse matrices. So in contrast to vector architecture, it hasn't got these features: no masking, no conditional execution, no vector length register as well. Now here comes the question: what was the advantage of vector length register when we were talking about in vector registers, vector processors? So we said that vector processor has got a vector length register and a maximum vector length register, which is a constant. right? Now what happens in vector processor is that if you want to change your architecture, if you want to change your design, so you were talking about initially 64 elements, but then you want to change your design, you included operations for 128 element. The only thing you need to do is change the vector register length from 64 to 128. Obviously this needs a lot of change at the hardware level, but from the instruction set point of view, you just need to change the maximum vector length, sorry, MVR, not MVR, MVL, uh, MVL over here, not MVR. So from the instruction set point of view, you just need to change the maximum vector length to 128 instead of 64. You don't need to introduce any new instructions. So same instruction, add vector vector, is going to work in the previous design, and it's going to work still in the new design. At the hardware level, obviously you are going to make changes. You need to have bigger registers, you need to have functional units that can work for 128 elements. That's another thing. But at the instruction set level, your same instruction can work. When you say your same instruction can work, this means you don't need to change the program as well. So your same program can also work. Keeping in mind, you just have to change some changes for the VLR and some other stuff, but majority the instructions are not going to change. When you're talking about instruction set extension, these are just extensions. So initially they were working on 64-bit numbers. Initially they were working on 64-bit elements, so they introduced some set of instructions. But when they changed their register size, so there is no concept of maximum vector length over here. If you're going to change the register size, you have to bring in new instructions. So for example, if you have add 64, which means you're working on 64 element, you have to introduce another instruction which is going to call as add 128. And if you're going to introduce double precision or other stuff over here, and you want to work on 256, you have to introduce another special instruction which will be called as add 256. So you're going to have 3 different instructions for add. 64 is going to work on just the 64 element. 128 is going to work on those elements. So you are keeping on increasing those number of instructions. That's the problem in SIMD. That it's not in comparison with vector architecture. First of all, it's nowhere close to the size of the vector architecture. The second thing is it hasn't got any masking. The third thing is no sophisticated accessing modes. The fourth thing here is there is no concept of the maximum vector length register. Each time you're going to change the architecture, bring in new instructions. The same program cannot work. So let's look at quickly DXP. I'm going to just go through that because we have less time left. So this was something that we did earlier. So I'm not going to go through that. How are we going to write DXP in SIMD? So the first instruction the same. That's okay. So what are we going to do in the next one is we are going to move the value which we have A in 3 more registers, F1, F2, and F3. So all these 4 registers, F0, F1, F2, and F3 are going to have value of A, right? So these 4 instructions are doing this. Once you are going to load it, then you are going to do an internal operation and store these values in 3 more registers. So all F0, F1, F2, and F3 are going to get the value of A. Because we are going to do 4 operations per instruction, so that's why we have done it this way. So this is so we are having 64-bit double precision number. So these are double precision registers, and we need to work on 4 double precision operations at one time, right? Then this instruction is same as this one over here. So now let's start with our first instruction, and this is a special instruction L.4D. Now that's a new instruction. Obviously, it depends on the architecture, but let's assume that we have an instruction L.4D. So what is L.4D going to do? It's mentioning a single register F4 over here, right? And then there is a register offset defined over here, which is for addresses. So it looks like a normal instruction, but it's not simple load. It's L.4D, which is that it's going to load 4 different double precision numbers in 4 different registers. Now, this is something which is implicit in this instruction. It's not written over here, but this is implicit over here. Is this instruction, what it's going to do is get this value, the first 0 RX, the first address, and store it in F4, the first double precision number, 64-bit number, and store it in F4. And it's going to take another consecutive location double precision number and store it in F5, and another one in F6, and another one in F7. So this L.4D is fetching 4 double precision numbers. It's fetching 4 double precision numbers in one operation. So remember, in vector operation we were doing 64 operations in one operation. Here we are doing it at a very small scale. We have 4 operations in one instruction. So L.4D is doing it in 4, and it's not mentioning any of these F5, F6, and F7 register, but it's implicit over here. Whenever you're going to talk about F4 and you're talking about 4D, the next 4 registers are also going to be reserved for this purpose. So it's going to load the first value, the second and third and fourth. So 4 register elements are 4 double precision elements are going to be loaded in a single instruction. Then what you are going to do is multiply it with F0. Now, when you're saying we are multiplying with F0, so it's not only F0 with F4, you're doing a corresponding multiplication. So F4 is going to be multiplied by F4, F0, F5 with F1, F6 with F2, and F7 with F3. Now, this is nothing mentioned over here, but again, this is implicit because you have introduced a new instruction, which is mul.4d. Now, this 4d here is meaning that you are working on 4 double precision numbers. So you just have to give the first register. If you say for F4 and F0, then this means F4 will multiply by F0, F5 with F1, F2, F6 with F2, and F7 with F3. As a single operation, you're doing, as a single instruction, you're doing 4 multiplication operations. Then you're going to load again the same thing, load Y into F8, which means F8, F9, F10, and F11 would be reserved for that. And then add F8 with F4, which means F4 would be added with F9, F4 would be added with F8, F5 with F9, F6 with F10, and F7 with F11, right? And then finally you're going to store it. So then these things are the same over here. So you can see what is the difference between a simple.
Sir, but in add F8 written is first. Then
Where is that?
F8 in add.4d. F8 coming first. Then it shouldn't start from F8, F9, F10, F11 instead of.
That's something which is implicit over here. That's something which is implicitly defined in this instruction, that if you want to add with .4d extension, this means that, and you just have to provide the first register name. So what's implicit over here is F8 would be added with F4, F9 with F5 as a single operation, and likewise F10 with F6 and F11 with F7. Was that your question?
Yes, sir.
And then it's going to be stored in F8, means that F8 is going to be now F8 plus F4, F9 is going to be F9 plus F5, F10 is going to be F10 plus F6, F11 is going to be F11 plus F7, right?
Yes, sir.
So you can see here there are special instructions like L.4d, mul.4d, add.4d, s.4d. All of these special instructions are doing 4 tasks in one operation. Compare that with vector, where we were doing 64 tasks in one operation. This is vector operation at a very small scale, but still it's a vector operation. It's going to be called as a vector operation. So this is going to reduce the number of operations because this loop is not going to run 64 times it was happening over here. It's going to run 64 by 4 times or 16 times, right? Because we are doing 4 operations in every iteration, so you just need 16 iterations, not 64 iterations, right? So this is an improvement over scalar operation is going to do the task quickly. Okay, so this is all about SIMD. So the main we have talked about SIMDs and difference with vector processor, how the programmed XP is going to look like, what are the instructions, what is implicit over there, how many registers. So it's taking the same floating point register and working on them, but in a different way. The underlying hardware has to be defined. These instructions are going to behave in a different way. All of this is going to change, right? Now we come to our last topic here, the GPUs. Last topic related to vector register. There's one more topic left, so I'm going to talk about that. Today we have got 6 students here. Two are not over here. Who are there? One of them is Iqbal Aziz. Who else is not here? Altaf. Okay, so two are not here. So what I need to discuss before I go for GPUs is your exam. So yeah, I've extended your date. So it's going to be on Friday now. Okay, that's a good news for you. The second thing is it's going to be online. Okay, it's going to be online means that you are going to get I think so 3 hours for doing the paper and half an hour for uploading it, or maybe yeah, three and a half an hour. That's what I remember. 3 hours for doing the paper and half an hour for uploading the results. Um,
Yes, sir. This is the news.
okay, then what else is
Sir,
there?
because the Jumma, what will be timing is strict 2 p.m. or
Yes, two to five, 2 to 5.
2 to 5 is the timing over here. If you are having problems in yeah, normally what happens is we have our prayers by 1:30. Most of the masajids here, it's going to be 1:30. It's going to start by 1:30, finish by 1:45 or something like that. You can find a masjid which is offering the prayer much earlier. At NED, we are going to start at 1 o'clock. The Jummah prayer here starts at 1 o'clock. Uh, yeah, but 2 would be the time, and if you are 5 or 6 minutes late, that could be adjusted because you're getting half an hour for uploading. Normally, you don't need half an hour for uploading. Okay, so three hours for doing that and half an hour for uploading. And then the important thing here is, because in the last class I discussed about going from lecture number 9 onwards to lecture number 15, that was for the physical test. So if you are doing it online, then it's going to be for the whole part of the for lectures, but uh, it's not going to be the whole all of that exam is not going to be covering the whole uh, lectures. It's going to be majority is going to come from 9 to 15, right? But a single question would cover the thematic part. So I'm going to have a single question as well covering the thematic part. But because what I saw in your midterm result, it wasn't very good actually. That the result that you have obtained is out of 50, but I've reduced it and considered it out of 25, but still it's not very good. So I need to give some more exercise, because that was an open book. I don't know why you did it wrong, why most of you did those things wrong. um,
So, what was the maximum marks in midterms, if you can reveal it?
okay, my midterm is going to 25. There were some quizzes that I took earlier. There are some assignments, and all of that class participation is going to basically include in those 40 marks, because the final of 60 marks. um, this means that I have to include questions from the earlier topics as well, right? But majority of it, like for example 50 marks, are going to be from the later lectures from 9 to onwards, and then 10 marks question or around that, is going to be from earlier topics, right? So because it's online, it's much easier for you to write the answers. You have to try to do as many questions as you can. No one did that. Maybe it was quite lengthy. That's why I've reduced that from 50 to 25. So 25 marks have been reduced. So at least you should have done half of that paper, right? I'm going.
So you are right.
If you have any problems there, then I can give you the solutions for that. But these questions were very easy. I mean,
Yes, sir.
for
Please do.
example, if you were talking about multiplication, we have discussed about those multiplication operations, the Booth's algorithm, base radix 4 Booth's algorithm. So you just have to go through that table, selected that particular number, and then you do that multiplication, verify that results. For division, the first thing I told you was that check for overlaps. If there are overlaps, overflows. If there are overflows, then you don't continue with that. And this is what was there. There was an overflow, and still you started
Yes, sir, there was an overflow.
with the division operation. Except for I think one student, everyone completed that part here. The other thing was regarding those three extra instruction floating point numbers. What I wanted was just give me an example, show me by adding two numbers, whatever you want, that 3 bits are enough. So what you had to do was just select a particular example, try to add them together, and just show me how it's going to perform and why more bits are not going to be adding anything more to it, more to the final result. So, and that was also for the case of when we're talking about the adder, the RCA, the ripple carry adder, and carry skip adder. You were supposed to give me an example which is going to show the benefit of the carry skip adder. And that was the example that we did also in the class, where we said that if you have got a number such that it generates a carry in the first level and ripples it to the last level and keeps on changing the result at each level, then this is the one which has got the worst case delay. In carry skip, this same example is going to give you only half of that delay, because it's going to skip most of those parts by giving the propagating the carry earlier than time. And this is the advantage. So you just have to give one example, and that was enough. So no one did that as well. um, what other thing was wrong? Then in two of those questions, you were asked to write the conditions. Those conditions were already with you. You just have to look for that, change the stages, and then write it down. Normally, I ask those questions for in an on-site exam, and students used to do that. But you already had those in your lecture notes, and you just have to see them, change the registers, and write those conditions. So I mean, that paper wasn't very difficult. I mean, I never asked you for a case study. In a case study, it happens is that you have to think a lot, and it takes a lot of time. All of these questions were very basic questions. Anyhow, so you just focus on the 60 marks that are going to come next week, inshallah. So just try to focus on those marks. Try to prepare more for that. Um, yeah.
Sir, regarding the midterm exam, you were saying that it was easy. Yeah, it was, but wasn't it a little bit lengthy? Would you comment on that?
I think so. You people waste a lot of time in division operation, for example. The first thing was check for overflow and write it down. The second thing was those floating point additions. You were a little confused, and those operations also don't take much. I've reduced it from 32-bit to 16-bit. So 16-bit additions, 16-bit multiplication were quite easy tasks. I gave you an example which had got the same exponents. So you don't have to shift anything. You just have to add them, subtract them together, right? And you just have to think about that and do that quickly. It wasn't very difficult. it was an open book, so you don't have to think of that. You just have to open that lecture note and go through that. But the thing is, if you have studied it, and you don't waste time in opening those lectures, and you can do it at your own. By my estimate, it was supposed to be done in 1 hour even. It could have been done in 1.5 hours. So that was, you were given more than that time. Okay, anyhow, so yeah, for some students it was lengthier, so I have also reduced 25 marks from that. I have reduced it from half of those marks are not included in your final answer, so that's something that is going to benefit you. Otherwise the percentage you would have
So
been
that means
changed.
you have scaled down the marks, right?
Not scaled down that marks, I have taken those marks out of 50, but I'm going to mention that as out of 25. So if
Oh,
you
okay.
have got, if you have obtained a marks, for example 10 marks, those 10 marks are out of 50, but 10 I'm going to include out of 25, so that's
Okay,
the
right.
percentage changes,
Okay, okay,
right?
okay, okay, yeah, fine.
Yes. Okay, so let's come to our last topic here, GPUs. So GPU stand for graphical processing unit. As you can see here, the whole idea behind vector processing is to do to have many functional units and do the same task on those functional units, same operation on those functional units at the same time. Now, the best case for implementing this data level parallelism is multimedia operations. Now, with the advent of these gaming industry, with the start of this gaming industry, and the amount of money that is they included over here, people need processors which are capable of doing things very very quickly, because they need a feel to do the things as real as possible. Because if you're developing a game which is not going to give you the result, if the correct response time or the correct you can say features that you are accustomed to seeing, then no one is going to play it. So you need a very good graphics and for good graphics you need a good experience, a natural experience. And for natural experience you need to include many more things which are computed at runtime, and that needs a computation power. For example, what you are seeing as my picture is I am having different light effects coming on my face. So because there are different light sources, because there are different structures, so some of these lights are much brighter and they are producing a different effect on my face. So one of my side is brighter than the other one. uh, if I get a different feeling, like for example, if a whole of my face is bright, and then there isn't any source, light source, and still my face is bright, you would think that this is unnatural, or this is not what you are trained on, you are accustomed to see. So you are not going to believe in that, and that won't be very much um, good for the experience of the user. When you are going to design something, or you want to run something, play something, watch something, you want to have a feeling which is as natural as possible. Now behind that, what happens is this is what is naturally happening. But if you want to design a game, then you have to do many calculations. Like a light source, if it's going to bounce off a glass, it's going to have a different effect. If it's going to bounce out of a wood, it's going to have different effects. So what people have done and research is they have found out the formulas for that, but these formula needs different calculations. There's air running in, there is light source of different type. So you need to include all of that and determine what that pixel intensity or color value should be, and not only for one pixel but for many pixels in an image, and keep on doing that on and on. So you need shadowing, you need texture filtering, you need everything which is there in a normal thing. So the light source, so all of that needs a lot of computation. And if you can do that, you need a very very fast hardware for doing that. A simple CPU cannot do that, because a CPU does one thing at a time. It's not built for cases like vector processors. So you need some a hardware unit which has got many functional unit, and you can just give a task which is a simple task, but you need more of those elements to do the task at one time. So GPU is the perfect thing for that. So a graphical processing unit is actually, if you go back in time, it's not related anywhere with CPU. It's related with the graphic cards that were initially there. So graphic cards evolved into graphical processing units. So it has its own memory. It has its own caches. It has caches for shadowing. It has caches for textures and other features, right? The main idea is that it should have simple processing units, but many of them. When I say many of them, that means thousands of them. So we are not talking about an 8-core system or a 4-core system. We are talking about thousands of cores. Obviously, those cores are not the same cores as an octa-core processor or a quad-core processor. These are very simple cores capable of doing just a very basic operation like addition or multiplication. But you should have hundreds or thousands of them, and if you have that, then you can accelerate the graphic operation in a much better way. So the whole idea behind GPUs is it's called as not SIMD, but single instruction multiple threads. So you're talking about threads over here, and thread is something which can be said as having many instructions. So it's single instruction, multiple threads. Multiple threads means that a thread is going to have many operations, and that operation is going to run a single instruction. Okay. There are two different programming paradigms, CUDA and OpenCL, that are implemented these days even for writing programs on GPUs. Now, what happens is that GPU in itself is a graphic processing unit, right? But since this is such a powerful unit that you can do many more tasks with that, not only graphics. So what people did in mid 2000s was that in 2005 and 2006 they started exploring GPUs for scientific operations, for engineering applications, and they thought that this is something which has got many functional units. Why can't we do these engineering operations on it, right? So they started to write their programs in the language which is supported by GPU, but it got very difficult for them to do or to map it over there. So NVIDIA introduced a language called CUDA, which was close to a high level language, and you can write your programs over there, and then CUDA is going to convert that program into the assembly language which is understood by GPUs, right? OpenCL is going to work on all the GPUs, but CUDA is only going to work for NVIDIA GPUs. So we are going to talk about just an example of GPUs. I'm not going to go through all of these slides because um, these are self-explanatory. I'm just going to go through just the internal architecture. Right, so this diagram here shows a GPU, the Fermi architecture. So you can see many similar blocks over here at this point. So each block is same as the other one. Then there are some DRAM interfaces, Giga scheduler, host interface. Host is the term in NVIDIA term referring to CPUs, right? So the GPU is called the device. The GPU is called the device, and CPU is called the host. So there's a host interface to interact with CPU. So GPU cannot run alone. So you need a CPU to initiate the transfer, but it has got its own memory. There is a separate cache for all of these blocks over here. So I'm going to describe this block later. This whole block is actually a streaming multiprocessor. We call this as a streaming multiprocessor. So there are 16 streaming multiprocessors if you can count them. So we have got 8 on this side and 8 on this side. So there are 16 streaming multiprocessor. Each multiprocessor has got many cores, right? So if you look at one of these streaming multiprocessor, you're going to see it's divided into two sets of 16 cores each. No, not 16. Yeah, 16. 1, 2, 3, 4. 16 cores each. Uh, two sets of 16 cores, which means 32 cores. So we have got 16 streaming multiprocessor, and each streaming multiprocessor has got 32 cores. So this is something like 512 cores. But that core is not the same as a quad core or an octa core processor that we see for ARM or Intel. This core is a simple core like this. So it has got its own dispatch unit, its operand collector, much like what we saw in the Tomasulo's algorithm or reorder buffer. So operand collector is just to check if you have your operands with you. Dispatch port is going to dispatch the right instruction at right time. Then there are just two units over here: a floating point and integer unit. If you want to do complicated tasks, you have got other units which are called as special functional units. These are 4 special function units. Like for example, you want to do square root, or you want to calculate the sign of any number, take the inverse of any number, right? So you need special function unit for that, and there are 4 special function units for your operations. But the core has got just two small units: a floating point unit which can do floating point multiply or add, integer unit which can do an integer multiply or add, and then there is the result queue which is going to store those result or connect them. The register file is quite big. You can see here we have got 32,768 registers of 32-bit each. This is a big register file. You have got 32,000 registers, each of 32 bits or 4 bytes. So that's a very big register file here. And this is for just one streaming processor. We have got 16 of these streaming multiprocessors. So you can see here the amount of hardware that is included. Interconnect network that is connecting with the shared memory, a 64 kilobyte shared memory, and an L1 cache which is going to be shared with these cores. So these, they are going to collect their operands, they are going to get that from cache, and then there is an interface to get it from the main memory or L2 cache, right? All of that is described over here. So I'm going to skip this slide. Now, in terms of GPUs, so as I mentioned that they were built for graphic operations, but for graphic operation is limited because it can do certain tasks and it's going to only work on enhancing the graphics. And this is what it was built for, so that's okay. But if you want to do engineering operations on that, for example, you want to write a matrix multiplication program, or you want to do some kind of image processing operation or weather forecasting or any other thing which needs a lot of resources, what you can do is make these GPUs as general purpose graphical processing units. So much like a general purpose processor, we sometimes have a term called GPGPUs. So GPGPUs means general purpose graphical processing units. This is a term which is used when you are going to use GPUs for engineering applications, and you need to program in such a way, right? So here we have got some different terms for understanding. Like grid is a program or code that you need to run on the GPU, right? Your main program. Then you divide that program into blocks. So a set of concurrent threads that can execute the same thread program, and they are going to cooperate to compute a result. And thread is like an iteration of a loop. So like for example, a DexP has got just one instruction in a loop. So that is a thread. That's going to, and if that is going to convert into 5 different instructions, all those 5 instructions are going to become a single thread, which is going to be scheduled on different streaming multiprocessor. So each thread, which is block, is going to is going to be identified. So thread blocks and threads have their identifiers, right? So these are in terms of the GPU programming model. So these are different terms defined over here. So for example, if we need to multiply two vectors of length 8192, we can write a simple program like this, which it's going to run from 0 to 8192. So this whole program is going to be called as the grid or the kernel. Now, it depends on the architecture, which architecture you have selected, because it has various number of string multiprocessors, and if you want to balance the load on every string multiprocessor so that all of them work on the same task, then it's a different thing. So what you do is break it down to thread blocks. So for example, in NVIDIA Fermi, you are allowed to up to 1536 threads. So because there are 16 streaming multiprocessor and we are thinking about utilizing all of them, so what we have is 8192 divided by 16, so we can have 512 threads per block. So we are going to break our program into 512 threads per block, and these threads are then collected together in another term called warps. So we are going to schedule them in warps of sizes 32 each. So 32 threads is going to make one warp. So that's the basic dispatching unit. So if you divide 512 with 32, you're going to get 16 warps. So you are going to break up your program into 16 such warps, which are going to be scheduled on a single streaming multiprocessor. And this is the whole picture. These are your 8192 operations, so threads. So what you have done is broken that down into thread blocks. So there are 16 thread blocks which are going to run on every streaming multiprocessor. So this is going to go to first one, and this is going to go to the 15th streaming multiprocessor. Each streaming multiprocessor has got 32 cores, and you are going to schedule that in 32 threads, which are called as warps. So 512 threads in each streaming multiprocessor, and you are going to have 16 such warps. So it's going to take 16 cycles to do the whole task in one streaming multiprocessor. And since they are all in parallel, so it's going to take just 16 cycles to do 8192 operations. So you can see how fast this is. 8192 operation in just 16 cycles. That's the speed. So because it has implemented that in different cores and running it on as much parallel as it can. The main thing in GPUs is it has got its own scheduler. So it knows how to schedule that. So it has got its warp schedule, and within that warp schedule, that is an instruction dispatch unit. So this diagram here is just showing you how is it going to be dispatched on a particular. So there are 16 CUDA cores and 16, so 32 defined in two different blocks of 16 bits each. So you have 16 CUDA cores separate, then 16 separate. So in total there are 32, but a warp of 32 threads is broken down into 16. So it's going to take 2 cycles to do this task. So one of them is going to be scheduled. One of them is going to be scheduled on one of them, and the other is going to be scheduled on other, and they are going to run in parallel. So it can also happen that thread block number 0 has got 16, and thread block number 2 has got 13. So you are going to schedule thread 1 and thread 2 over here. That's possible. Then there is a special function unit. There are 4 of them. If there is some special instruction that is going to be scheduled along with, so you can have 2 operations starting every cycle. So in this first case, what we are doing is floating point add and load together. Then we have got floating point add and reciprocal together. Then we have a floating point multiplication and 2 floating point multiplication. Then we have addition and addition. Then we have a move and a load together. and then multiplication and sign started together. So we can schedule just 2 operations in every cycle, right? And then it's going to run that. I'm not going to discuss about the details about that because that's not part of our course. I'm just going to give you an introduction of what that is and how it's going to be done and how can we write a DXP program and how is it going to be different than a vector processor. So let's come to first of all CUDA in a very simple term. So it's called a compute unified device architecture. Again, device means GPU and host is the CPU. So there are some limitations of CUDA. It was developed by NVIDIA for its own GPUs, and this was released in order for programmers to write their own program. So it's something similar to a C language. You can look at the structure is similar to C language, and you can write your program as if you are writing a program for C language. So these are some advantages of CUDA. So let's just skip that. There are some limitation as well. Like for example, there are some deviations with the standard floating point architecture, floating point standard that we studied. In GPUs, there are texture rendering caches as well. It's not going to use that. It's limited in its strength, so it's only going to use the basic features. I have skipped the memory model of GPUs. In this case, if you're going to study the memory model, then you're going to study there are different caches in GPUs. There are different caches for texture. There are different caches for shadowing. So they just take the data related to that particular operation. So for if you're running your program CUDA, then it's going to discuss about anything about texture cache or shadowing operations. Okay, so let's look at a very basic program. Like we want to array of 8 elements. So we have got 8 elements, and we need to take the square of that, right? So you multiply them together. So what's going to happen is you're going to have your program in GPU, in CPU. It's going to initiate that. It's going to first of all transfer that in the GPU's memory, and then it's going to initiate. Then the GPU is going to spawn the threads, and then threads gets the number, and then it's going to run on these elements. So you have a choice of running 4 threads. So each thread is going to take 2 squares, or you can do it in 8 threads, where every thread is going to take just 1 square. So what's happening if you are going to do it as 8 thread is every thread is going to get an identifier, and again there are different dimensions to that, X, Y, and Z dimensions. The main thing that I want to come at is what is the program going to look at the device level. So at the device level, at GPU level, the code is that in terms of CUDA is that you are going to define a variable myID, which is going to be that thread ID, the X dimensional ID, and it's going to work on only that ID. So this is the code which is going to which every core is going to get, and it's going to get a different thread. So it's going to work only on that element which is there, right? Then there are different you can say specifics for block ID. You can have a 2-dimensional block as well. So you can introduce another term as block. So instead of having a 1-dimensional thread, you can have a block ID defined as well. So there are 4 threads in this block and 4 threads in this block. So that is another way of distinguishing the threads. You have, again, the block can be also in X, Y, and Z dimensions. So this is another version of the same program written in a different way, where you're talking about having a block size of 4. So you're defining the thread ID in terms of block ID into the block size plus the thread ID. So again, here the thread IDs are from 0 to 3. So that's why you are going to get different IDs. Again, it's going to do the same thing over here. Here what we have defined is how to define a 2D grid or a 1D grid. So what at the programmer's level you are assigned how you can manage those threads in blocks. So here what we see here is we are having thread blocks. So 3 into 2 thread blocks, and that is 6 thread blocks, and each block has got 15 threads. So this is determined by this instruction here, that we are planning to have 3 into 2. So it's a two-dimensional thread block, and each block is going to have 5 into 3, or having 15 threads. A one-dimensional 4 into 6 would be something like this, where everyone is going to have 6 threads, and they are going to be 4 blocks. Right, so this is something left to the programmer to decide, so how you're going to manage the threads, but then threads are going to be scheduled in this way. Now let's come to DexP. So you know what double into ax plus y is going to look like. So this is going to be your DexP version. So again, you need to define the id, and then the main task, that if it's less than n, so you are doing the main task. So it's something like similar to a C code. You are defining double a into x plus y, just as you are doing in at the high level language. The only thing is it's going to get an identifier, and you have defined it over here. And when you are going to invoke this instruction, then you are going to define these terms, that what is the n block size. So n block is going to be n plus 255. That n value is going to come from the user, and then you are going to define that you are going to do it 256 threads. So you are going to have 256 elements over here that you are going to add together. So the main thing that I want to discuss over here, I'm not going to go into details of how this has happened. The main thing is that it's quite simplified. First, if we talked about vector architectures, then we talked about the SIMD architecture. Again, they were more concerned with the assembly language or instructions, but here you can see you have support of CUDA, so you don't need to go into the details. You just need to know how to write your program. So your main concern is to write the program for a single iteration, and that's it. The other things are specific details. How many blocks do you need? How many stream processors are you? So this is going to generate the DexP program having 256 threads, and each thread, and they are going to be n blocks over here. N blocks is something which you are going to define. So since there are 64 elements over here, so this n blocks is going to be something like, so we have got 256 threads, and we need to work on 64 elements. Okay, so they are actually more than 64 elements over here. So I'm not sure about what, if the n block size is 4, then there are going to be 4 such ones, and each having 256 threads. So it's going to work on 1024 elements, right? Each of them is going to get 256 elements. So in total, it would be 1024 elements that's going to work with if n blocks are 4, right? So, and each one gets the value of a, x, and y. So x and y is going to be provided to it, and the integer n, which is going to be the maximum. So it's going to check whether that value is there. And so the main thing is quite simple. That's the main thing I want to focus on. That this is the about GPUs, and they are extensively they have quite more hardware than a vector processor, much more connected, different the memory bandwidth is quite high. They can do many more tasks. Register file is quite big. So, and writing programs in them is also quite easy, right? So this is about GPU, and we are not going to focus more on the internals or how to write the program. The main thing is I was just talking about how it's going to be much easier to write the programs in at GPU level because of CUDA. Okay, so that comes to the end of our lecture. The whole course. So that was the first time that we did it as an online course, and this is our 16th lecture. The last topic of that, loop level parallelism. You can do that yourself as well. It's not very difficult. Loop level parallelism is to find out whether a loop is parallel or not. So we called a loop as parallel if it hasn't got any loop carry dependency, and that is a very simple thing to check, because what you can see over here is every iteration is different than that is independent of the other iteration. So you can see here we have 1,000 elements, and all of these elements are going to add s to it, and they are not concerned with what's happening to the other element. They're not getting any results from any other iteration, so we say that this loop is independent, or in other words, it's a parallel loop. So if the loop is parallel, then you can take the benefit of data level parallelism. That's the main thing. Let's talk about another example. Now, is this loop parallel? Now, one way to look, so if you have any answers, if you don't have any answers, then one way to look about that is to go with different values of I and see what's going to happen in first iteration, what's going to happen second iteration. So I'm just going to write the first iteration code. So I is 0. So that means A1 is equals to A0 plus C0. And B1 is equals to B0 plus A1. That's it. This is the first iteration, right? What is going to happen in second? Just writing two iterations is sometimes enough. What's going to happen in the second iteration?
Sir, but it's not independent.
Yeah, I'm going to come to that. A2 is equals to A1 plus C1. I'm just going to come to that. And B2 is equals to B1 plus A2. Now you can see here there are different dependencies. Yeah, you're right. There are different dependencies. So what are dependencies over here? So the line here mentions the end of the loop. So we can see here there are dependencies within this loop. So we are not concerned with that. As you can see over here, this A1 is getting the results. But we are not really concerned with that. When you're talking about loop level parallelism, you are more concerned with dependencies between iterations. Now, when this program is going to run on a sequential processor, you're going to see that it runs one iteration at a time. So these are the sequence of instructions that it's going to see: first, second, third, fourth, and so on. So the order should be the same as well, because if you're talking about A1 over here, that result is over here, and if you're talking about A1 over here, that result is actually this one over here, right? So you can see a result has come from a previous iteration. So if a result has come from a previous iteration, this means this loop is not parallel. It has got loop carry dependencies. Now, if it has got loop carry dependency, it could be made as parallel, but they can be procedures for some of the loops, but not all of them. But we are going to see if this loop can be made parallel. The main thing is it has got dependencies within iteration and with different iterations as well. Okay, so the same thing for B as well. So you can see both A and B are taking a result of the early iteration. This means that you cannot do this thing prior to this one. So the order has to be preserved. And if you don't have loop level loop level parallelism, then this means GPUs or vector architectures are not going to help you out, because there we are assuming that iterations can run independently. So that's why we are going to schedule them in different cores or different vector units, but here that's not going to happen. Okay, I'm going to just clear this thing. Right, so there are two different dependencies as we have discussed. So that is there. So this is, as you know, this is there is a loop dependence, so this is not a parallel loop. Let's take another example. We are going to do the same thing with this example, but since we have got less time, so I leave this for you to do. I'm just going to talk about that. So it would be A naught is equals to A naught plus B naught, and B1 is equals to C naught plus D naught. That's it. So we can see here, if you go to the next iteration, then it would be A1 is equals to A1 plus B1. And since we have calculated B1 in the first iteration, there would be a dependency over here. So if I talk about this in this term, B1 is going to be calculated in the first iteration, and A naught is going to be calculated in the first iteration. But in the second iteration, what we need is A1 and B1. So where are we going to get this B1 from? That's the first iteration, right? So again, and that's going to repeat for the other iterations as well. So B2 would be calculated in the second iteration, but it would be used in the third iteration, right? So that's the problem over here, that again there is a loop carry dependency. So this loop again is not parallel, but can we make it parallel? Now, because it hasn't got any dependency from A naught on, you can say that there is no dependency within these two instructions. What we can do is shift the loop boundaries in a different way. Now, since we are more concerned with loop carry dependencies to make a loop parallel, what we can do is try to have this part in one iteration, and likewise this part in the second iteration. So we need to convert this thing. So one of the instruction, the first one is going to be separate, and then last one is going to be separate, and then we can have the loop converted in a different way. So what we are trying to say is the first one, like A naught is equals to A naught plus B naught. That's our first instruction, and this is as a separate instruction. Then what we do is write this for loop, where we have our first instruction as this one, which is going to be I plus 1 or bi in any words. If you can start with I is equals to 1, that's going to be fine as well. So you can do it anyway. And your second instruction would be the first instruction, so that would be A. But now since you have changed it, so you wanted to work on A naught. So if now I is going to start from 0, this is actually A0 you have already done, but in the second iteration you have to find A1. So that should be again converted to AI plus 1 is equals to AI plus 1 and BI plus 1. So what we have done here is made this as our first instruction. We have separated the first instruction of the first iteration separately. Then we have run a loop. I'm going to talk about how much time do we need to run this. That's another thing. But now the second instruction of the first iteration becomes the first instruction, and the first instruction of the second iteration becomes the second instruction. This means that because that was dependent on, that was passing the loop boundary, so you have included that in the same iteration. So now there is an iteration, there is a dependency which is within that iteration but not outside that iteration. So you've converted this program in a different way. Lastly, what you're going to do is it's going to run 99 times, not 100 times, because you have done one instruction for the first loop separately. The last thing left is to do the last instruction separately. So the last instruction would be then the last value, which is going to be 99. So B100 is equal to C99 plus D99, right? So the whole program for that is here. This is the changes that we need. the first instruction and the last instruction are written separately, and then we have got a 99 times loop which is now parallel. Because there is no circular dependency, we call it dependent circular when the statements they are dependent on itself, and when S1 depends on S2 but S2 does not depend on S1. So we have S1 which is depending on S2 but S2 is not depending on S1. That's why there is no circular dependency, right? So had there been a circular dependency, you couldn't have changed this loop into a parallel loop. Okay, so this was about loop level parallelism. There are other examples, you can go through that yourself. There is another way to finding whether a particular loop is dependent or not. If you have your indices defined in a fine form, which is a into I plus b, then you can find the dependencies between different iterations of a loop by a simple test which we call as a GCT test. So you just need to find out whether so for example, you have got two numbers, two um, indices, and you want to find out whether they are going to be same somewhere. So what you do is convert that into an affine form and do a simple GCT test. And in a GCT test, what you do is take the GCT of C in A, and you can see whether it divides D minus B. So let's take an example. So I need to find out whether this loop is independent or not, right? Now, as you can see, this number is written in a different way, but it still is in a fine form. So there are two different indices for X. One is 2 into I, another is 2 into I plus 3. So I need to find out whether in any iteration from 0 to 100, is there going to be some iteration which is dependent on an earlier iteration, or are all of these iterations independent of each other? That's what I need to find out, right? So for that, I need to convert that. I need to first of all have these indices in a affine form. And an affine form is something like that where you have A into I plus B, right? So in the first one where you have 2 into I plus 3, the value of A is 2, the value of B is 3. In the second one, you can have C and D. Same way, C is J plus D. That's the second one, which is also running for a particular unit. From the first one is from I, the second one is J. Here the C is 2 and D is 0, right? So what the test that you have to do is find the GCD of C and A. So GCD, greatest common divisor of 2 and 2, is always going to be 2. And you must see that evenly divides D minus B. So D minus B is 3 minus 0, which is going to be 3. So is 2 going to be evenly divided by 3? So if the answer is yes, then it has failed the test. But if the answer is no, then this means that this loop is parallel. So since 2 cannot be divided evenly by 3, this means that this is a parallel loop. This is a loop. This is a loop having no dependency between iterations. And if you want to test it out, you can take different values of i's. For example, take the value of I as 0. So you're going to have 3, and here you're going to have 0. If you increase that value 1, so here you are going to have 5, and here you are going to have 2. So you can see all of these are going to be even numbers, and all of these are going to be odd numbers, and so they are never going to be mixed up together. So you are always producing an odd number as an output and always taking an even number. So all the iterations are always going to be different, and this can easily be done using this GCT test. So this brings us to the end of our course. That was the very last topic. And if there are any questions, you can ask me on the slide.
Yes, sir.
Yeah.
My question is from regarding final paper, that what will be a pattern? Either it will be a numerical or theoretical, or
because it would be online. Because it would be online, I won't be asking you for definitions, but there would be similar questions like we had in midterm. Like there would be some problems, and majority of that would be problems or your own opinions. So I'll be asking more on what to do in this case and what to do in this case and something like that, so that you get different answers. There was a case of two students copying a solution even in this class. Um, I got to know about that, but that there was a single student, so that's good that you did yourself, except for one student who copied one of the parts, not all the whole thing, but one of the part from another student, and he wrote it incorrectly. That's the main thing. If you are going to copy it, you don't know what's happening. You try to just copy, and so you make mistakes, and it's easy to detect that. And what happens is you then get 0 marks for that. So don't try to copy it. Write whatever you think you can think of. um, I'm going to give you marks for that, so don't worry about that. So even for midterm, your sessional marks, these are not your sessional marks. The sessional marks are depending on your assignments, uh, your class participation, and other things as well. So but in the final, those 60 marks, you have to work a lot for that.
Sir, can you share the solution of midterm if possible? So,
Okay, I'll do that.
if possible.
Yeah, I'll do that. Any other thing? What is the please limit the course? I would have limited it that to from lecture 9 to 15 had it been on-site exam, because I know that uh, you don't have to consult the book for that case. But now if you have to consult the book, and for that case, there what was happening was that the final exam wasn't having so much percentage. So now you have got 60% for the final exam and 40% for the rest of the session. So this is then an uneven distribution. So to make that even, you have for 60 marks you have to include the whole course. So what I'm going to do is I'm going to have one question from lecture 1 to 8, that as I mentioned, around 10 or 12 marks for the first 8 lectures, because we have studied that earlier as well. So in order to balance both of these contents, and then the remaining is from going to start from the memory topics.
So that would be arithmetic, you said, most probably.
Yeah.
Thank you, sir.
Okay.
Sir, can you also share the chapters 2, 3, and 4?
I have already loaded chapter 2, 1, 2, and 3. 4, I'm going to upload 4 today. Right, exercises included. 4, because 4 started with in chapter number 4 there are exercises related to vector and SIMD and GPUs. So you cannot do all of those questions, because we have discussed only a limited part of the section. Some of the questions related to affine forms or finding dependencies between iterations, that you can do. So
Sir, only chapter number 1 is there. I'm checking right now.
no, I have already uploaded chapter 2, 3 as well in the book in the classroom. That's uploaded with the different names, not as chapter 2 or 3. It's with let me just check. Uh, Under the classwork, you have book material, and in that book chapters you have instructional algorithm. That's chapter number 3. Instruction pipeline introduction. That's an appendix of an earlier book. And then you have the computer arithmetic, chapter 1. Chapter 2. Okay, I'm going to upload chapter 2. That was about memory. I thought I had uploaded it, but okay, chapter 2 is not here. I'm going to upload chapter 2 and chapter 4. Okay, I'll do that. I thought I had uploaded my memory, but okay, I'll do that. Yeah, the deadline for that has already gone for chapter 1 assignment. One student has submitted it to me. That those questions were for your own working. So if you're going to work on that, and you're going to get some problems, you're going to ask me about that. But I didn't get any questions, so I have assumed that no one has worked on that, or maybe all of you have worked on that and they were so easy. So both are possibilities. Right. So the main thing is the solution is also available on the net. So I know that. So I'm going to do nothing by checking that or taking your assignments. I just wanted you to do that and get some results. And if you're going to find some problem, ask me the question. Okay. Right. So I'm going to
Sir,
end it now.
sir, Imtiaz, sir. What about
Yeah.
the case study?
What about what?
Case studies. You said in midterm.
Case studies, yeah, because we have got 3 hours. Case studies normally need more hours. So you have to first of all think about that question in a different terms. Normally, such a question is going to design the whole thing. So you need at least 1 to 2 hours for a particular question because it's normally a lengthier question. You have to study the whole architecture and then you are going to give question answer to those problems. So it takes a lot of time.
So,
So
sir,
I'm
we
not
can expect that the case studies won't be.
not at that level, but a small opinion type questions like what is your opinion on this, or what are the benefit of this versus this. These are the questions which are mostly going to come.
Okay, sir.
Okay. Okay.
So,
Thank you all. Thank
any
you all.
last thing, if you would please, anything that is I was looking at this Tomasulo's algorithm.
Mhm.
In that, we see that when the algorithm is almost done, there are multiple tables that get free from the
Mhm.
values.
Mhm.
So, how if it comes in exam, then how are we supposed to do that? Because we don't have to write it and then erase it and make multiple tables.
Yeah. If it comes in exam, I'm going to give you um, you can say a free page for that which has got many different blocks representing every cycle, and that is going to be an empty cycle and an empty block representing one cycle. So if you want to go for another cycle, you have to do it in another page, right? If I'm going to give you that, then I'm going to give you space for that as well, so you are going to write it in different places.
Okay, okay. And it would be a written paper just like the meds.
Yeah, just like the previous one, the midterms, you have to write it down by hand.
Okay, okay. Okay.
Okay. Right. So we are going to meet inshallah on next Friday. So the timings are 2 o'clock, 2 to 5. So get all your papers ready. Free papers. Write your roll numbers. There would be a top sheet, I think so, shared with you. Will be shared with you by Eli Baksh. You have to just fill in that top sheet. That would be your first page of uploading. Okay. Try to do it yourself. That's the main thing. Don't copy it from anyone. Don't try to discuss it with anyone. Try to write your own opinions. Okay. Okay, Ji, thank you all. Now we are going to
Thank you,
go for.
sir. It was a nice time with you, sir.
Thank you. Nice time with you
Thank you,
also.
sir.
Thank you. Thank you.
Allah Hafiz. Allah
Allah
Hafiz.
Hafiz.
Thank you, sir. Allah Hafiz, sir.
Allah Hafiz.